Hello, now we're going to do a problem on surface area. Set up but do not evaluate two integrals that give the surface area generated by rotating the curve y equals the square root of x cubed plus 1 from the point 0, 1 to the point 2/3, rotated about the y-axis. I have a little drawing of this situation down below, just a little piece of the rotation, not the full thing. And before we jump into it, we need to remember all our formulas. We know that surface area is built upon arc length, and the arc length is, if you're doing it with respect to x, is the integral from a to b of 1 plus dy dx squared dx, or if you're going to do it with respect to y, it's the integral from c to d of the square root of 1 plus dx dy squared dy. Now, when we're looking at surface areas, when we look at this drawing, we can remind ourselves, okay, if we cut this out part and laid it out flat, we can see that its area, the surface area, equals the circumference times the arc length, right? The circumference is the length around, and the arc length is the length along the curve that's being rotated. And so we know for circumference, we know is 2 pi r times arc length. And in this case, when you're rotating about the y-axis, your radius is x. And so going down to my formula, the arc length about the y-axis, I want the integral of 2 pi x times arc length. That formula doesn't change much. If you're rotating about the y-axis or the x-axis, the only difference then would be your radius would be y instead. So there would be the integral of 2 pi y times arc length. Both of these are done over whatever the appropriate domain is. And so that's where we're going to start. So we know, so let's first do this with respect to x. With respect to x, first, we want to talk about our domain. Our domain has to be in terms of x, and so x ranges from 0 to 2. And then we need to know our arc length with respect to x, and for that, we need to find dy dx. And so let's find dy dx. Y equals x cubed plus 1 to the 1/2. And so dy dx equals 1/2 x cubed plus 1 to the negative 1/2 times 3x squared. Now we're ready to put together our surface area formula. The surface area is going to be the integral from 0 to 2 pi x times the square root of 1 plus 1/2 x cubed plus 1 to the negative 1/2 times 3x squared, all squared, dx. And that's the integral. We don't have to do anything more with it. It said set up, but do not evaluate it. And so now we want to move on to doing the same thing with respect to y. First thing let's do is figure out what our domain is. Again, we want to figure out our domain with respect to y. So we want to look at what do our y range from. Our y seem to range from y equals 1 to y equals 3. And we also need to know, instead of dy dx, we need to know dx dy instead. So I need to solve this equation for x. So I'm going to square both sides, subtract 1, and then take the cube root of both sides. So x equals y squared minus 1, all raised to the 1/3. third power. And then when I look for dx dy, I just take the derivative with respect to y. So I get 1/3 y squared minus 1 to the negative 2/3 times the derivative of the inside is 2y. At this point, I'm ready to start setting up my integral. My surface area equals the integral from 1 to 3, 2 pi. Now we're doing this with respect to y. I'm sorry, we're rotating about the y-axis, so our radius is x. So 2 pi x times the square root of 1 plus 1/3 y squared minus 1 to the negative 2/3 all times 2y all squared all underneath the square root dy. And we got one little problem with that answer. It's not all with respect to y. It's all with respect to y except for that pesky little x there. We don't want that x there. And so we need to do one more line. One more line where instead of the x, we erase the x and replace it with something with respect to y. Okay, what is x? What is that x value in terms of y? And for that, we go up here and we say, oh, I see what x is. X was y squared minus 1 to the 1/3 power. And there are our two integrals, both of which, if evaluated, would give the surface area, neither of which I particularly want to evaluate. They both look pretty messy. But the good thing is, this problem just asked us to set it up. Thank you very much. See you in the next lecture.